On Monday, we looked at the titration of a strong acid with a strong base, and now we're going to look at the titration of a weak acid with a strong base. So we're looking at 25 milliliters of formic acid, HCHO2, with sodium hydroxide. These concentrations are equal. And so the first thing we're going to do is look at the volume of sodium hydroxide needed to reach the equivalence point. So we have 25 milliliters of the acid, and it's 0.100 molar, and the sodium hydroxide is also 0.100 molar. And we want to know the volume. Of course, can you guess what the volume is? 25. 25 milliliters. I'm just going to call it HA. No, I did have something backwards. Like, wait a minute, this is not going well.
The first conversion.
Oh, yeah. So I had the middle one right. I did the first one wrong.
Yeah.
So milliliters down here. And then over here we've got milliliters and 0.10 millimoles of NaOH. And everything cancels out. We get 25 milliliters. Anytime you're doing a stoichiometry problem, and titrations are always stoichiometry problems, you should look at it like this and not use M1V1 equals M2V2, because that is for dilutions. This is not a dilution. In a dilution, you don't have substances changing into other substances, because what gets lost is this mole ratio in the middle. And the reason people do that is because if your mole ratio is 1:1, you're okay, right? But instructors know that students like to do that, and so we like to put examples on the exams that are not 1:1 to catch the people that do that. So just be aware of that. Okay, so the volume at the equivalence point only depends on the amount of acid, the moles of acid, not on its strength. So this is a weak acid. It's not going to ionize completely. That does not come into the calculation of an endpoint. Okay. So let's look at the initial pH before we add anything. So the initial, I don't know what that was. The initial concentration of the acid is 0.1. The acid, hydronium ion is about 0, and the conjugate base is about 0. And so we're going to look at this decreases by X, these increase by X, and so we have these guys at the end. And so we can say that Ka is equal to X times X divided by 0.100 minus X. And here Ka is 1.8 times 10 to the minus 4. You can use your solver, or you can do X is small. X is small takes this guy out. So then we have The square root of 1.8 times 10 to the minus 4 times 0.1. So if we do that, then x is equal to 0.00424. Well, actually here. And how do we know if this is an okay thing to do, the x is small? It needs to be less than 5% of that. So I've got this number in my calculator. I'm going to divide by 0.1, multiply by 100, 4.24%. Okay, that's close, but the rule says 5. So then what's the pH? Well, the pH is the negative log of that. pH is the negative log of 0.0042426. And come up with 2.37. Any questions? That should be pretty okay, right? Because there's things like that that could be on the exam tonight. Just using equilibrium constant. So now we're going to look at our first addition of sodium hydroxide. So we're looking at how hydroxide reacts with the acid, and it's going to produce water and the conjugate base of the acid, right? So we're looking at the stoichiometry in moles. So the hydroxide that's being added, you know what, I'm going to do this in millimoles because I am really tired of all the zeros. Okay, so how do we find the millimoles of sodium hydroxide that have been added? We take 5 milliliters times 0.100 millimoles per milliliter, and that's 0.500 milliliters. I'm sorry, millimoles. Right? So we have 0.500 millimoles. And how many moles or millimoles of the acid do we have? Well, we have a volume of 25 milliliters, and the concentration is 0.1. So we have 2.5 millimoles of acid. So 2.50, millimoles of that. So we're going to look at how the hydroxide is neutralizing the acid. And so here the hydroxide being added is less than the acid that was present. So all of the hydroxide is going to get used up. And we end up with 0 of that. We're going to use up 0.500 millimoles of the acid. So we're going to end up with 2.00 millimoles. And then over here, we started with none of the conjugate base. When that acid gets neutralized, we're going to form 0.5 millimoles of the conjugate base. Any questions? I'm going to figure out how many millimoles of my acid I have, how many millimoles of hydroxide I've added, and I'm going to treat that as a complete reaction and see what happens. Now we've got a weak acid and its conjugate base. This is a buffer now. We can use the Henderson-Hasselbalch equation, but we really should do this in terms of molarity instead of millimoles. So we've got, so our concentration of HA then is 2.00 millimoles divided by the total volume. 25 milliliters plus 5. Right, so that's 30. So we got 2 divided by 30. So 0.0667 molar. And what do I say for my hydrogen ion concentration? Essentially 0, right? And then how do I find this concentration? That's the conjugate base. So I have 0.5 millimoles of that, 0.500 millimoles, divided by the new total volume, .0167. That's really a mess. Do you see how I did that? This is what we were doing earlier in this chapter, right? This is a buffer, and so chances are good we can use the Henderson-Hasselbalch equation. So I'm going to try to sneak that in here. So the pH of this is going to equal the pKa. So pKa is negative log of the Ka. Plus the log of the base over the acid. So this is the base concentration, 0.0167, and the acid is 0.0667. Getting 3.14. Any questions? The Henderson-Hasselbalch equation only works when x is small. We're not actually calculating x here, so the 5% thing doesn't work so well. But we did learn that this ratio needs to be between 0.1 and 10, right? One can't be more than 10 times larger than the other. And this is okay. Any questions? I don't know where that came from. I didn't do that. guys are so quiet. It's kind of scary. Tense. Okay, so we keep adding. 10 milliliters, 12 and a half, 15, 20. So to calculate the pH here, we would do the same process. What I want to look at is the 12 and a half. This one right here. So after adding 12 and a half milliliters, I've got an equal amount of the acid and its conjugate base. I am halfway to the equivalence point. I've added half as much sodium hydroxide as I need to neutralize all of the acid. So I've neutralized half of the acid, right? So here, the amounts in moles or the concentrations of these two are going to be equal. So if we look at the Henderson-Hasselbalch equation, oops, not the acid. If the base is equal to the acid, then the log of that is 0. And we end up with the pH is equal to the pKa. So that's this point right here called the half equivalence point because we're halfway to the equivalence point. At that point, the pH is the same as the pKa. Let's look at what happens when we get to the equivalence point. Again, I don't like this. Well, how many millimoles of stuff do we have? We got 25 milliliters of 0.1 molar acid. So that's 2.50 millimoles of the acid. And I've added 25 milliliters of 0.1 molar sodium hydroxide. 25 milliliters times 0.1 is 2.50 millimoles of sodium hydroxide. And this starts out at 0. So now we see that we have equal amounts of the sodium hydroxide and the acid, which is a definition of the equivalence point. And so these are going to react with each other, and we're going to end up with essentially 0 and plus 2.5 of that conjugate base. So now what we have is we have a solution containing the conjugate base of a weak acid. That is an ion that acts as a weak base. So we're not going to be using acid ionization constants anymore. We're going to look at the base. Okay, so we've got A minus plus H2O is going to make HA plus hydroxide ion. This is A minus and that's HA. And that is base ionization. So we can look at this and say, okay, well, I have 2.5 millimoles, but wait, I need this to be in molarity, right? So I've got 2.50 millimoles of my weak base, and what's the total volume of my solution now? I started with 25, and I added 25 more, right? So 2.5 divided by 50, 0.05 molar. So as I make the ice table down here, I've got 0.0500 molar of that conjugate base. And I'm saying I've got 0 of the weak acid and essentially 0 of the hydroxide ion. So we're going to do the minus x plus x business again. There's not enough space. So Kb is equal to A minus over HA times the hydroxide ion concentration, which is the things we've got down here. X squared over 0.0500 minus x. And what does that equal? They didn't give us Kb, they gave us Ka. So Kb will equal 1 times 10 to the minus 14 divided by the Ka. So 5.556 times 10 to the minus 11. Let's cross our fingers, hope that x is small works. So then x will be the square root of Kb times the 0.05. One 1.667 times 10 to the minus 6. Is that the hydronium ion concentration or the hydroxide ion concentration? It's the hydroxide, right? It's easy to forget about that. So from that, we're going to calculate the POH. POH 5.778. So pH is equal to 14 minus that. .22. What was the pH at the equivalence point when we titrated the strong acid? It was 7, right? This one is going to be a little bit basic because when we neutralize this weak acid, we form something that acts as a weak base. Any questions about that? That's why there wasn't room. I did it on the next slide. That's fine. What about 30 milliliters? Well, 30 milliliters times 0.1 is the number of millimoles of hydroxide. So that's 3.00 millimoles. And 25 milliliters of 0.1 is still 2.50 millimoles. Now we see that the acid is smaller than the base. That's going to be our limiting reactant. So we're going to end up with none of that. We're going to lose 2.50 of this. No. 3 minus 2.5 is not 1.5. It's 0.5. Okay. Is this a buffer like it was before the equivalence point? No, it isn't. Because what we've got here is we've got some hydroxide ion and we've got this conjugate base. So we're going to calculate the pH here like we did at the equivalence point. We have to turn these into molarity. So the 2.500 millimoles, our new volume is 25 plus 30. So 0.04545. So we're going to be looking at the base ionization. Yeah, that's right. Plus hydroxide ion. You see why we have to do that? We've neutralized all of the acid. We're not looking at a solution of a weak acid right now. We're looking at the solution of the conjugate base. So this is acting as a base. So again, we're going to have to use our Kb here, and we're going to write the equation for this acting as a base. Initial change equilibrium. So the weak base was 2.5 millimoles, which we found out was 0.04545. And the hydroxide was 0.5 millimoles. divided by 55 milliliters. Zero point zero zero nine zero nine. What's the concentration of the acid? 0. We neutralized it. So what we're doing here, I'm adding sodium hydroxide, and I'm going to assume that this is going to react completely and go all the way to the other side. But then I know that if I have some of this, there's going to be an equilibrium. After we push everything to that side, then we can look at the equilibrium. So this is going to lose, and this is going to gain, because that can't get any smaller. If you put minus x here and plus x here and use a solver, it'll give you a negative number. And if you put the negative number in there, it'll give you the correct concentration. I'm not recommending that, but if you see that, that's why. But this can only go to the right, because this is 0. So minus x and this will be plus x plus x so KB is equal to x times 0.00909 plus x divided by 0.04545 minus x. And we don't have to recalculate the KB. That was 5.56 times 10 to the minus 11. So let's use x as small again, and these guys go away. So then x is going to be equal to our KB, 5.56 times 10 to the minus 11, times 0.04545 and divided by 0.00909. 2.78 times 10 to the minus 10. So is this X my hydroxide ion concentration? It isn't this time. So here's hydroxide. At equilibrium, it's 0.00909 plus X. Well, we can add that to 0.00909. It's not going to change anything, though, is it? So hydroxide is 0.00909 plus 2.78 times 10 minus 10. Now, if we think about that, isn't that what we were assuming when we did this? That X is small? And so that adding to that doesn't make a difference, and so we could have saved ourselves some time. So that is still going to be 0.00909. So I want the negative log of that. So my POH is gonna be 2.041. My pH is 14 minus that. This is just a horrible mess. I'm sorry. I'll blame it on not having my cookies. It seemed like a good idea at the time, now not so much. 11.96. Which looks like that. Yes?
So, technically, when we did all of the molarity like that one,
Mm-hmm.
we don't actually have to divide it with the milliliters because then it will cancel out.
Yes,
Let me see.
but I don't recommend doing that.
And also, can we use just the Hasselblad? Why cannot we use just this?
So we can't use Henderson-Hasselbalch here because it's not a buffer. When you're titrating a weak acid with a strong base, the part, that flat part at the beginning, this part, that's a buffer. But when we get here, it's no longer a buffer, and it does not return to being a buffer over here. So what would happen here if if you took this 0.5 and didn't divide it by 55 and tried to do this calculation, you're not going to end up with the right answer. Because we have a concentration times a concentration, and so those would both have the conversion factor, the volume, and this would only have the volume in there once. I knew there was a reason. Any questions? You can keep adding 35, 40, 50 milliliters. These would be the same kind of calculation. You would look at how many moles of acid and how many moles of base you had, and limiting reactive problem, push that as far as it can go, and then look at the weak base ionizing. In all of these, though, we're going to end up with X being small and not mattering, actually. So here's the overall pH curve. So this region, before the equivalence point, this is the buffer range. That's where you can use Henderson-Hasselbalch equation. Up here, we have an excess of hydroxide ion. Here at the equivalence point, we're looking at just the weak conjugate base in terms of calculating the pH. Calculating the initial pH, we're looking at the weak acid. Any questions? Okay. A 40 milliliter sample of 0.1 molar nitrous acid is titrated with 0.2 molar KOH. Calculate the pH at the equivalence point. So we have HNO2 plus hydroxide, right? And that's going to go, well, actually, let's just, sodium, no, it's potassium. Doesn't matter, but it's one of those. So we're going to end up with a product of water and potassium nitrite. Now, normally what we do is we leave these spectators out, because this doesn't really look like a conjugate base, does it? It looks like an ionic compound. So let's leave that spectator out, because it wasn't doing anything anyway. So this is our A minus, and this is our HA. So we had 40 milliliters of 0.1 molar HNO2. 40 milliliters times 0.1 is going to give me 4.22 millimoles. Okay? And I'm at the equivalence point. How many moles of hydroxide do I have? The same, right? I would have to have the same number of moles of hydroxide, because that is what the equivalence point is, where we've added a stoichiometric amount of hydroxide to neutralize all the acid. So here they're matched up, so this is going to end up being 0. This is going to end up being 0. And over here, whoops, this started out at 0. And so we end up with 4 millimolars of nitrite ion, which is a weak base. So at the equivalence point, we have a solution of a weak base. So nitrite ion plus H2O is then going to be in equilibrium with nitrous acid and hydroxide ion. I have the millimoles of this conjugate base. I need the molarity, though. I need the volume, don't I? 40 milliliters of acid times 0.1 molar times 1 mole to 1 mole times milliliters, 2.2 millimoles. Okay, lesson number 1, turn on the calculator. Works so much better when you do that. 20 milliliters. I need this volume because I need the total volume so I can calculate the concentration, right? So the concentration of NO2 minus that I'm looking at here is 4.00 millimoles divided by the total volume. 40 milliliters plus 20 milliliters. So that's 60. 4 divided by 60, 0.0667 molar. So these guys neutralized each other, made a 0.067667 molar solution of this. And now I'm going to look at the pH of this weak base solution. So that's my initial concentration for the nitrite ion. The nitrous acid is 0, the hydroxide is essentially 0. So Kb is going to equal x squared divided by 0.667 minus x. And what is the KB? Well, it's 1 times 10 to the minus 14 divided by the Ka. So the Kb is equal to 1 times 10 to the minus 14 divided by the Ka. And so that's where this number came from. It's like I read up there. Let's try x is small. So then I'm looking at the square root of KB times 0.0667. Two 25 ml samples of unknown monoprotic acids, A and B, are titrated with 0.1 molar sodium hydroxide solutions. The titration curve for each acid is shown below. Which of the two weak acids is more concentrated, and which one has the larger Ka? For which answer? More concentrated. Yeah, so, gosh. I don't know how that even happens. So to answer the more concentrated question, what we're going to do is we're going to look at the volume at the equivalence point. And we don't need to have it exactly, but just close. It looks like it might be 34 or so. And over here, this one is less than 25. This took less sodium hydroxide. The sodium hydroxide concentrations were the same. So this one is more concentrated. So that one's more concentrated. Does that make sense? Mm-hmm. Now what about the Ka? What was the pH when we titrated a strong acid? It was 7, right? 7 is right here. Both of these are higher. The pH at the equivalence point looks like it's about there. Looks like it's about there. So we could look at the pH at the equivalence point, and they're looking about the same, aren't they, actually? So that's not really helping very much. Because we're not supposed to have to like measure things carefully here. We could do that to prove to ourselves that these are both weak acids because the pH at the equivalence point is above 7. Where's another point we can look for the Ka information? Initial pH. The problem is one's more concentrated than the other. Half equivalence point. So the half equivalence point is halfway to the equivalence point. About 34, so about 14? No. 17. Yeah, 17. So about here. And this one was, I don't know, maybe 23. So that one's over here somewhere. The pH there is equal to the pKa. Which one has the smaller pKa? B. So this is a smaller pKa. How does that relate to the Ka?
It's equal.
Well, the pH is equal to this. But if this is not asking about pKa, it's asking about Ka. So you can't remember. I can't remember. Let's pretend we don't know. So the pK is the negative log of the Ka. So let's try the negative log of 1 and the negative log of 0.1. So the negative log of 1, I don't know what that was. Negative log of 1. That's 0. The negative log of 0.1 is 1. Smaller Ka, larger pKa. Okay? That was way too many Ks. And that can be like super confusing. But the reason is because of this negative here. The log of a smaller number is going to be a larger, it's going to be a more negative number. So let's say I was taking the negative log of 10 to the 1 or the negative log of 10 to the 3. The log of 10 to the 3 is going to be 3. I'll just have to splice these together. So what about titrating a weak base with a strong acid? The calculations will be similar. The initial pH, you're looking at a weak base solution. Here, you're going to have a buffer again, and the half equivalence point is going to give you, the pH will give you the pKa. At the equivalence point, then you're starting to have an acidic solution. You're looking at the conjugate acid. Okay, what's the pH at the half equivalence point in the titration of a weak base with a strong acid? The pKb of the weak base is 8.75. So we're titrating a weak base. At the equivalence point, do we have a solution of weak base or weak conjugate acid? So here's our base, and we've been adding acid to it. And now we've neutralized all of it. So we have none of this left and none of that left because these were equal at the equivalence point. So we have a solution of HB, this base. I'm sorry, this is a weak acid. So then we're looking at what happens to that. Right, so this is going to be, we're gonna have some concentration here. The initial will be some number, and these will be 0. A number minus x and x and x. And if we were doing this calculation, we'd want to use the Ka. Oh, I'm sorry. Like, this is really a weird conceptual question. Missed a word. The half equivalence point. Thank goodness. Okay, so, sorry about that. That was a bad detour. Okay, at the half equivalence point, titrating a weak base, is the pH equal to the pKa or the pKb? It's still the pKa. Because pH is equal to pKa plus log of the base over the acid. We're wanting pH, not pOH. At the equivalence point, these are equal, and so this drops off. pH is pKa. So the pKa here is,
But we need the half equivalence.
this is at the half equivalence.
You said at the equivalence point of the log.
I'm sorry, yes. At the half equivalence, these are equal. So it should be 5.25. Titrations of a polyprotic acid. So here we're looking at sulfurous acid. Here's the first Ka, and here's the second Ka. If those are different enough from each other, you will actually see 2 equivalence points. The volume needed to reach the first equivalence point will be half of the total needed to reach the second. So the first equivalence point, you've neutralized one of the protons on the acid, and you go another amount equal to that, and you neutralize the second one. Consider these 3 titrations. So the volumes and the concentrations are all the same, and they're being titrated with sodium hydroxide, same concentration. So I'm just trying to identify what's different about these. So we have a monoprotic weak acid, a diprotic weak acid, and a strong acid. Which statement is most likely to be true? All 3 titrations have the same initial pH. Will that be true? No. That's not true. Because the strong acid will have a lower pH than the weak acids. All 3 titrations have the same pH at their first equivalence point.
I don't think so.
No. Because the strong acid will be at 7, right? And weak acids, at the equivalence point, you have a solution of the conjugate base, so it will be above 7. all three titrations require the same volume of sodium hydroxide to reach their first equivalence point. Yes. It is the only one left. The volume and the concentration is the same for each of these. The concentration of the base is the same. They're going to need the same number of milliliters.
Professor?
Yes.
But if it was, okay, can you rewind on the one that was the half equivalence point?
Oh, the previous one?
Yeah. This one?
That one?
Why do we have to subtract it with 14? I mean, no. How is it that when we subtracted with 14 we got the answer? Don't we have to divide it by 2? Because the PKB is equal at the half. I don't get it.
Okay, so pKa plus pKb equals 14. Because Ka times Kb equals 10 to the minus 14.
And at the half equivalence point, what is special?
So at the half equivalence point, we're not going to do anything with the number 2. But at the half equivalence point, so the moles, here we're titrating a base. The moles of base, and how to say this? So if we have X moles of base, at the half equivalence point, we've added X over 2 moles of acid. So we've neutralized half of it. So we do the stoichiometry part, and we end up with, in our ice table, the base concentration being equal to the acid concentration at the half equivalence point. So, because this is a buffer, Henderson-Hasselbalch equation tells us that if the base is equal to the acid, this is 1 and the log of 1 is 0. So the pH will equal the pKa when those concentrations are equal. So when we titrate a base with an acid, things are turned around, but they're not exactly opposite, right? My brain wants to say, well, the pH must be the pKb, right? Because it's a base. I think we'd find that the pOH would equal the pKb, but that's not what we're ever looking at. So you can measure or monitor the titration with a pH meter, but it's a lot faster and easier to use an indicator. So the indicator is something that changes color. It's going to change color at the end point. So the end point is when the indicator changes color. If we choose our indicator correctly, the end point and the equivalence point would be the same. If we choose badly, they won't be the same. So here we see our solution is clear, we're adding, and here it's switching and the color is just starting to change, and after that, it's the other color. So most indicators are, maybe all of them, they are weak organic acids. And the organic acid is different in color than the conjugate base. And that's a really cool thing that's beyond the scope of this class. But, so this is phenolphthalein, which is a very common indicator. So this is the acidic version of it, which is colorless. And the basic version, this bond has been broken here. And we lost, this, well, a couple of different things happen actually. This is the basic version and this is pink. And so here we see the color of it at different pHs. So we're seeing some pink color at pH 8. If we're titrating a weak acid, is the pH likely to be near 8? Yeah, because it's going to be a bit above 7, right? So what we see is that indicators are going to change color within a range of 2 pH units centered at the pKa. So pKa plus 1, pKa minus 1. So at pH equal to the pKa of the indicator, you're going to have the intermediate color. At a higher pH, more basic, you're going to have the color of ion minus, and down here, you're going to have the color of the acid version. So phenolphthalein goes between clear and like fuchsia, right? This one, this is methyl red. This one goes between red and yellow. So as the pH increases, here we're getting into this intermediate color. And then we go to the other color. So this is a table that's in your book, which gives a whole bunch of different indicators. And they've all got kind of crazy names because they're all organic acids. Some of them are a little easier, like crystal violet, that obviously says nothing about the structure of the compound, right? Whereas 2,4-dinitrophenol tells us about the structure of the compound. Some of them, I mean, you thought phenolphthalein was hard to say. You know, some of these are just really, really weird. So how would you pick an indicator? You want the pH range to correspond to your equivalence point, right? So for weak acids, it's going to be in this, 8, 9-ish range here. It's going to be above 7, right? And so, orthocrystalline, that might actually go a little too soon. But phenolphthalein is a really good one for that. Thymal blue is also good. And that's the second choice for people who have color issues and can't see the pink. I have some of those in my family. The thymal blue is easier to see. This one, the thymal blue actually has 2. It's a diprotic acid, and so it has 2 different places where it changes color, and so does alizarin. So we're going to do an unknown weak acid experiment, and one of the things you're going to have to do when you determine what your acid is and what its pKa is and stuff is you're going to have to choose 2 appropriate indicators for titrating it. Why do most of them have colors in their name? Well, most of these names are what we would call common names, right? And so, I mean, what are you going to call this compound that turns bright blue when you put it in base? Blue something, right? Yeah. So there's, several blues. There's thymal blue, and there's bromothymal blue, so that's got bromine on it. And then there's bromocresol purple, bromophenol, right? So there's a bunch of different things that would. On this chart, oops. This one, I'm really not sure what color it's changing from and to.
Red.
It's like
It's going from red.
it's going from red to red orange, and these two up here too. Like what? I don't know.